see here. So I want to talk about the, well, in your course planner it said it's calculus of curves, but the truth is it's the calculus of paths. And by path I mean some, we give in a time and we output, some vector of functions of time. So like x1 of t, xn of t, generally speaking, in n dimensions. But to start with here, let me just talk about n equals to 2. So, I'm supposing we have a path where we have, x is a function of time, y is a function of time, like that. That's our path. And so, essentially, well, some folks are more fussy than others, but I'll give you this as a definition. dr dt is just equal to dx dt, dy dt. So you just differentiate each component function separately. The integral of r of t dt would be the integral of x dt, integral of y dt. You could also make that a definite integral, and you just do like this. All right, so there, that's basically it. The derivative is done component-wise, the integral is done component-wise, and there just are all kinds of things we can say about this, as you'll see. I'll write out one example here, and then I'll dive right into the notes. So if I had r of t equal to, let's say, t comma t squared, then dr dt, so I d dt dt, comma d dt of t squared, oops, which is 1, 2t, and if I was to integrate this, that would be like integral of t dt, integral of t squared dt. And one thing I should mention here is we do need to have different constants for each one. So like I have 1/2 t squared plus, let's say, c1, and 1/3 t cubed plus c2, right? So in other words, you could write it as 1/2 t squared, 1/3 t cubed, plus some constant vector for this indefinite integral. So, this how it works. It's actually pretty simple, and yet it's tremendously useful. I'll explain to you in this this lecture and the next how we can use this to capture the physics of curves and the physics of paths, acceleration, velocity, speed. All this can be described using this calculus. Like already, if this is the position of a particle at time t, this is the velocity of the particle at time t. Speed is the magnitude of the velocity. So like the speed of this particle would be the square root of 1 plus 4t squared, for what it's worth. But anyway, we'll talk more about that later. Let me go on here. And I'm going to try to get away with this. Setting for the camera. I think we can get away with it. Let's see here. So the start of the chapter, I'm mostly talking about the later application to the geometry of curves, where we'll get to that in a later lecture. Calculus for curves, here it is. Here's the definition stated for I guess for 3 dimensions to start with. It's just like I did for 2, right? We also use prime notation, like a prime is d dt is d dt. The second derivative still means differentiate twice. One thing everybody always has a little bit of trouble with is finding the tangent line to a curve. So if we want the tangent line in 3 dimensions, it's going to be a parameterized line, right? So we take the base point plus t times the direction vector, but this time the direction vector we can get from the tangent line. Let me zoom in a bit on that. Let's see here. So, you know, we've got some space curve, and trying to picture here this limit. You're looking at points closer and closer to get to the base point, and taking the limit as h goes to 0, eventually you get to the tangent line doing that. So this is the more careful definition of the derivative I was alluding to before, but practically speaking, we can just take the derivative of components in here. Here's an actual example of finding the tangent line for a specific example. I think it's kind of a 2-dimensional example masquerading as a 3-dimensional example, but you'll forgive me for that. So let's look at that for a second. So we have the curve, really the path t squared 0. I said find the tangent line at 1, 1, 0. So first of all, there's a typo here. That's supposed to be like that. This is actually a printout of my 2014 notes, so don't take too much from the page numbers here. The page numbering is like a little bit off, but the examples are pretty much the same. I'm sorry, I'm being cheap. I didn't want to do color printout of all my notes again. I haven't found out the color printer at school yet, so my apologies, guys. Anyway, so I figure out time 1 is when we get to that point. I find the velocity by differentiating, and then I plug in time 1 to get 1, 2, 0 for the direction of that tangent line, which we're going to get from the velocity evaluated at the right time. And so once I have that, I can write down the parameterization of the tangent line as 1, 1, 0, that's the base point, plus t times 1, 2, 0, which is the direction given by the velocity. So again, that's a parameterization of the tangent line at 1, 1, 0. And as I said, the curve and the tangent line are both in the z equals 0 plane, which is plotted below. So I've used time for the parameterization of both the curve and also the tangent line. The way I have it set up right now, the red curve, when we get to that point of tangency, for the red curve, it's time 1 rather, right? But time 0 is when the tangent line gets there. So if you thought about these as the paths of 2 different particles, the particles would not collide at the point of tangency, because if you have a particle traveling the tangent line, at time 1, it's up here somewhere. At time 0, it's there. Now, if you want the colliding tangent line, in other words, you want the tangent line to be such that when you're at the point of tangency, your path and your tangent line collide. If you think of them as particles, you can just do this. You do the same thing that we did, basically I'll do it for this one, 1, 1, 0. And then you just do, instead of t, you do t minus 1. And everything else the same. So what that does is it just shifts the time for the tangent line such that when we get to time 1, the tangent line is at 1, 1, 0. So they collide. But anyway, there you go. The next example is, pretty standard calculation. What I'm showing in this next example is that, sorry about the camera being kind of wobbly, it's because I forgot my usual mount at school, and I've got the camera mounted in a somewhat precarious manner. On a t-square, actually, with some, anyway, I'll shut up. So what this shows is that, if we wrote this example in a different notation, what this is r equals to a constant vector r naught plus t times the vector abc, right, which I'll just call for lack of an imagination, I'll call it vector big V. So big V is the constant vector ABC, right? And so what this calculus here shows is that dr dt equals, I mean, I'm showing you a different way to think of the calculation, dr naught dt plus ddt of V. So in other words, this is going to be 0. This is going to be 1. And we just get V as the answer. Because basically you can pull the constant vector out of the differentiation, and you can, you know, the constant vector differentiates to 0. Here it's multiplied by t, so you can think of the vector as pulling out of the differentiation. See, that's my V. Okay, so sometimes it's helpful to be able to think of calculus at the level of vectors rather than components. That's why I say that. Here's another example. I am differentiating 1t cosine t and then integrating it, and then integrating it from 0 to 1. The next example, I have e to the t times an unknown function of time, and here's an unknown function of time evaluated at t squared. And so here we see the chain rule in action and the product rule. So the purpose of these examples, guys, is mostly to intimidate the student into reviewing Calculus 1, because what we have here is a kind of a reminder that, hey, there's stuff in Calculus 2 that, you know, maybe you remember, maybe you don't. Actually, we don't always do everything in here in this course, but I'm just trying to encourage the students to review calculus if they've forgotten. Okay, so here's my little talk about that. Anyway, you guys are good on calculus, I'm not going to worry about that. But again, when you're differentiating a path, you still have to do all the regular calculus. Like when you differentiate, oh, look at this, I've got x's where I meant to have t, you know. That's just a typo, that's supposed to be t. Maybe I fixed it in the more recent version of the notes, let's hope. Anyway, this one's kind of neat. Here I actually have 0 cosine t sine t, 0 cosine t sine t as my path, and then I differentiate it, and I get r prime as that. And what I've done here is I've pictured the circle as well as the velocity at different times, right? It's always going to be pointing tangent to the circle. All right. Here's a question about two curves and then finding the angle at which they intersect. So if you have two curves and you want to find the angle at which they intersect, what you do is, like, here's curve 1, right? Here's the point where I'm going to make them intersect. Here's curve 2. Oops, pull that down a little bit. Like that. And so each one of those, so it has a, you know, let's say R2 prime, and we could picture the velocity vector like that, R1 prime. So the angle between the velocity for curve 1 and the velocity for curve 2 is going to be the angle between the curves at that point of intersection. That's how we define angle between curves, right? And so that's what I'm calculating here in this example. I have two curves, twisted cubic, and I'm not sure what that is. Maybe a helix. Well, it's not a helix. It's something anyway. I don't always have a name for the paths we work with here. So I calculate the velocity for each path, and then I figure out that they intersect at time 0. And so if you plug in time 0 into this, you get 1, 0, 0, and you get 1, 2, 1, right? And then we can find the angle between those two vectors as we have before. We take the dot product, calculate the magnitudes. That gives us that 1 is √6 cosine theta. So theta is inverse cosine of 1 over root 6, which apparently is 66 degrees. So that's the angle between these two curves where they intersect. So anyway, and then I'm also just commenting that you know, if we calculate the derivative to a curve, it gives us a sense of the geometry of the curve, right? So that's the point of this next example here, partly. The next example is about a helix. So here, cosine sine t is the helix, and if you differentiate it, you get minus sine t cosine t1. So it's like the velocity vectors, they're always pointing upwards, and they just kind of like wrap around, you know, the curve like that. All right, anyway, get to the point here. There's lots of really nice properties. Oh, I'm sorry, I'm getting out of order here. This is the definition for n dimensions. One of my better students complained bitterly that I had put definitions for 2 dimensions, for 3 dimensions, and then for n dimensions, but that's how these notes are structured. I kind of revisit the material either in 2 and 3 or in n dimensions. So if you have a strong sense of deja vu, that's the reason. But again, the definition is that you you differentiate component-wise and you integrate component-wise. And in my slick notation, it's even easier. I suppose it's easier. I should have told you to take some Dramamine, some for motion sickness here with this one today. I'm sorry about this wobbly camera. But in the x hat notation, this is a path, and so we differentiate by just differentiating the component, and likewise we integrate by just integrating the component. So yeah, and then I have a few examples in n dimensions, which I'll let you read. Oh, finally a theorem. Hooray! So the fundamental theorem of calculus for space curves is this. Come on, behave. Stop wobbling. All right. Fundamental theorem of calculus for space curves is that when we differentiate an integral with variable bounds, we just get back the integrand again, and also this is sort of like FTC part 2. The integral of a derivative is the value of the thing being differentiated and evaluated at the bounds. And the proof of these actually make decent test questions because they're really simple. And they're simple in the sense that these are immediately obvious if you already know the corresponding theorems for one dimension. So the derivative of this integral of a vector is so this is just notation. This is equal to that sum of component functions. Then I use the linearity of the integral to pull out the sum, and so this. Let's see here. This right here is, let's see here. What is that? Oh, the first equality is the definition of derivative of a vector valued function. The second equality going from here to here is just the definition of the derivative of a vector valued function. And then the third equality is I'm just using the fundamental theorem of calculus part 1 for each component function. And there you go. So, maybe the notation's intimidating here, but just to, if you don't understand it, just try to go through these proofs in like just 2 dimensions if this notation is troubling to you, so like, I'll do 2 dimensions here, the integral of like, d dt, and I'll like use a little f and a little g for 2 functions, right? So by definition, that's the integral from a to b of df dt, dg dt, so differentiate component-wise, right? But then, by definition of the integral, we integral from a to b, df dt, dt. Sorry if this is too small. Integral from a to b of dg dt, dt. So that's the definition of the integral of a vector of two functions. And then we use the ordinary fundamental theorem of calculus part 2. That's f of b minus f of a. This is g of b minus g of a. And then you can group these, right? We've got f of b, comma g of b minus f of a, g of a, and that's what we set out to prove. That, I mean, it's in a different notation here, but this proof I just did is exactly this proof. It proceeds by starting with differentiating component-wise, and then integrating component-wise, applying the fundamental theorem of calculus to the jth component, and then regrouping things to obtain the function at g evaluated at b and the function evaluated at a. And that, my friends, is a sign error. So, hope that makes sense. Yet another example. So here are some of the rules of calculus for space curves. Some of them will be familiar. Derivative of a sum is sum of the derivatives. You can pull a constant out. And integration also has that nice linearity. I'm sure I'm at the right level of zoom. Yeah, we're okay. This one here we'll use a lot in the upcoming lecture. First of all, if we've got a function times a vector, there's a product rule. If we've got a dot product, there's a product rule. If you've got a cross product, then there's a product rule. If you have any kind of product, there tends to be a product rule, all right? And it's usually the proofs of all of these basically is just the product rule for calculus 1 playing nicely with how we define these products, either by scalar multiplication, by dot product, by cross product. Here, let's look at the proof. So for the derivative of the scalar product, here's the proof. So we f times a vector, we differentiate it. First of all, going from here to here, that's the definition of derivative of a vector value function. We differentiate each component one at a time. Then this going from here to here is the product rule of calculus 1, because f times aj is just a function. It's a product of functions of time. F and a sub j are both functions of time, so this is a product. We use the product rule. And then the next step is just I'm pulling that constant function out of the sum, and this is just basically go from here to here is product properties of finite sums, and how we add vectors, and how we scalar multiply. But grouping things, that's the a vector, and that's the derivative of the a vector again. So there you have it. That's that product rule. And next up here is the proof of the product rule for the dot product. So we have the formula for the dot product is the sum of j equals 1 to n of a, j, bj. So we this is a derivative of a sum, so it's the sum of the derivatives. And then we do the ordinary product rule on the product aj, bj. That gives us this. And then I use properties of finite sums to rewrite it as two sums. And then tilt my head and squint and say, wait a minute, that's dA dt dot b, and this is a dot db dt, and there you go, that's the product rule for the dot product. The product rule for the cross product is pretty, not too bad if you have the right notation, and I do. So derivative of a cross b is the derivative of this, because that's the formula for the cross product. Remember that the epsilon, ijk, the Levi-Civita symbol, these are just plus or minus 1 or 0. They're constants, they don't depend on time. So we treat them as such in the differentiation. Step 1 is the derivative of a vector is the derivative of done component-wise. Then I pull that constant epsilon ijk out. I use the ordinary product rule to change this to that. I then regroup terms and identify once more that I have cross products. Notice that the order matters. Basically, you have the derivative hit A first and then B second, and you've got to keep track of that order. Notice that properties of cross product would say like this is minus B cross dA dt. I mean, I don't know why you'd want this formula, but here it is, minus dB dt cross A. If you switch the order of the cross products, it introduces minuses, you know? So, now, that said, I would be remiss if I did not show you a simpler notation that we sometimes use, the prime notation. So like A dot B prime works like that. A cross B prime works like that. So prime notation is still useful for vectors. And this is a very nice physical example about angular momentum. So angular momentum in physics we can define by the cross for a mass is the cross product of right here. This is the definition. Angular momentum is the mass times the radius vector cross the velocity. That's the angular momentum. And if the net force is F, we also know that F is equal to ma. We learned that in physics, right? This is Newton's second law. And torque, well, torque is defined by the cross product of the radial arm and the net, the force applied. So you can calculate the time rate of change of angular momentum, dl dt. So that's ddt of m r cross v. And now we can use that cross product rule that we just derived, which says that that's m dr dt cross v plus r cross dv dt, right? But notice that dr dt is exactly the velocity again. So this first term is really velocity cross velocity. What is velocity? Any vector cross itself is 0, right? So that piece dies, and we're just left with r cross ma. But that is the net force also by Newton's second law, so we've got r cross f. And r cross f is the torque, so by definition. So what we have is that the time rate change of the angular momentum is given by the torque. So, for example, if the torque is 0, that means that the angular momentum doesn't change. It's said to be conserved. So when would the torque be 0? Well, like if the force is in the direction of the radius, then this is going to be 0. And that happens for gravitational forces and more generally central forces, forces which are directed along the radius. Those kind of forces have torque 0, and so angular momentum is conserved. Another nice example, really, benefiting from our struggle to prove the product rule, is this one. If we have a vector which has length 1, then a dot a is 1, right? If that's true for all time. And so when you differentiate 1, you get 0, but when you differentiate a dot a, you get dA dt dot a plus a dot dA dt, which, what does that mean? Well, these simplify, right? This is equal to 2a dot dA dt, because you can group those together because dot products commute. So if that's equal to 0, that says that a and dA dt are perpendicular. So that's actually really, really important to our study of calculus, of geometry of curves. We'll see upcoming lecture. There's also, I noticed the chain rule in an example before. Here's the generic chain rule. If we have a vector valued function composed with just a function from real to reals, like this, then the chain rule says you do df dt, the derivative of the vector valued function evaluated at the inside function times the derivative of the inside function. So, and the proof of that is straight up just the chain rule applied component-wise over and over again. So it's a lot like the ones we've already done. Another notation, you could write it like this: d dt of f of g of t is df dg times dg dt. Here's a specific example with f being that, g being that, and here's the derivative of the composite. So anyway, we'll need this chain rule again as we study arc length and reparameterization of a curve. See, because this would be an example of like a reparameterization. You're thinking about trading, in some sense, trading t for g. G, you could think of like g as being the new parameter in some sense. So this says that the derivative of the reparameterized curve is related to the derivative of the original curve in a very specific way, just by the derivative of the reparameterization. So we'll need this later. So that's pretty much it for calculus of curves. I mean, in a nutshell, it works just like it already did for you. And we just have a few new wrinkles because we have dot products and cross products, and so we also learned some product rules for those, and they're exactly what you'd hope they would be. They're very simple and easy to remember. So thanks. I'll start again. I think next up is geometry of curves, but I've forgotten at the moment.